We're going to look at proving Pythagorean trig identities. Now, this is not commonly taught in high school to prove something, but it's good to know, and maybe it'll help us make sense of stuff. And really, it's also practicing trig identities, okay? So we have our triangle here, okay? And I want you to think of this as the height of this triangle is along the y-axis, and the base of this triangle along the x-axis, okay? And you can honestly think of it almost like a Cartesian plane with a circle, okay? I'm just going to draw a little quick example here. Think of it kind of like this, and this is how they want you to think of this idea. Is if I needed to find, this point here, I can build a triangle, okay? This would be my x, this would be my y, and technically from the middle to the outside is known as the radius of a triangle. Or sorry, not triangle, of the circle. Good. So with that being said, this is the radius, okay? This is our x, and this is our y. Think of it as like a triangle on this side instead. We've just moved things around a little. Also, this side where r is, that's the hypotenuse of a right-angle triangle. We're always building right-angle triangles, okay? So now that we've labeled this, I need to write the three basic trig, primary trig ratios, they're called. So for instance, sine theta. Excuse me. Sine theta is known as opposite over hypotenuse. Okay. Now, when we're solving for angles, we're usually solving for this angle in here, which would mean this angle. This would be our theta. Okay. So sine theta is opposite over hypotenuse, which our opposite is our y, and our hypotenuse is our r. So it's y over r. Does that make sense?
Yeah.
Okay. This is just strictly labeling. With that being said, cos theta is adjacent, okay, do it in green, it is adjacent over hypotenuse, which gives us x over r. And then finally, tangent theta is opposite over adjacent, blue, okay, opposite over adjacent, which is y over x. You okay with that? Okay. Using this same triangle, there's a rule called Pythagorean theorem. That's it. Sorry, I almost forgot there. And the way this rule is written out, I'll make a little smaller triangle here. The way this rule is written out is the idea, and we'll kind of shrink our stuff here. We have our x, our y, and our r, is that they would write it as this: a squared plus b squared equals c squared. Well, the c is the hypotenuse, okay? So this is technically our c. I'll use highlighting instead. So that would be our C side. And the A and B aren't as important. You can interchange them, but we'll call this our A, and we'll call this our B. Okay. And the idea, a lot of times it's shown in a proof to look something like this. When you square something, you essentially build a square. So they're saying this square and this square together would be equal to, see if I can set it up, this square. Okay, that's one of the ways they kind of they visually show this this proof here. Not too important for what we're about to do, but just give us a visual. Let's move that line away. Good. So, with that being said, okay, we can interchange the A, B, and the C with what we've called things. Okay. So, what did we call side A? According to this color here. Excuse me.
X over r.
Okay, you're going right into this. Let's focus on just straight up substitution. So the A side is our y.
Okay.
So that will be our y squared. Okay. The x side is our b. So x squared is equal to the r here is our hypotenuse, which is our c side. So r squared. So we now have this y squared plus x squared equals r squared. Okay. Same thing as Pythagorean's theorem. What we do want to do though is we want to set this equal to 1. Okay, and right now it's equal to r squared. So what I'm going to do is you can, whatever you do to one side of the equation, you can do to the other. I'm going to divide this side of the equation by r squared. And that means I've got to divide both of these by r squared. Okay, now on the right of the equation, r squared divided by r squared will equal 1. Y squared over r squared, I don't really know, but that does remind me of something. Y over r is equal to sine theta. The only thing is they've squared both, so we can square our identity also. So y over r can be replaced, y over r, with sine, and because they're squared, squared theta, okay, plus X over r, oh, x over r reminds us of something also. X over r was our cos. The only difference is they're squared, so we square our cos, and we get cos squared theta. Now, I highly doubt they're going to make you walk through all of those steps, but that is one of the proofs. From there are technically two other Pythagorean identities. We'll take this identity. This is the main one. And this is, we can, off of this one, we can build the other ones. So just like we did with the r squared in this example where we divided everything by r squared to set it equal to 1, well, I can turn this term into the number 1, or I can turn this term into the number 1 by dividing by the term itself. Okay. So in the first example, I guess we'll do it in blue. Sure, we'll do it in blue. We're going to divide, we'll call this the first example, everything by cos squared theta. Okay, cos squared theta, and divides cos squared theta. So with that being said, I'm going to do some of my identity proofs. Well, the first one here, cos squared theta divide cos squared theta, do you know what that's going to be?
1.
1. That's 1. Sine squared theta over cos squared theta is similar to the quotient identity, sine over cos. Sine over cos is equal to tan. Yeah, so sine over cos technically equals tan. I know I shortened that there. And since they're squared, we just got to square tangent. So we get tangent squared theta plus 1 is equal to. And we need to know the reciprocal of cos squared theta. Do you know what the reciprocal of cos is? Excuse me.
Of cos?
1
over secant?
Yeah, and now since this is 1 over cos,
Just secant.
Yeah, it's just secant. And again, it's squared. And the reason... now in this one, both were squared. I can square the number 1. What does that do? Does it change the value? No. It leaves it as 1, so it doesn't make a difference. So think of them as if they were both squared, and hence we got to make secant squared theta. And then to set it equal to 1, it's usually written as 1 equals secant squared theta, and then we just bring tan over, subtract tan squared theta. Okay? So that's our, I should call that number 2. That's number 2. This is number 1. And finally, number 3. Okay? Same start. Sine squared theta plus cos squared theta equals 1. Start the same thing. This time, instead of dividing by cos, we divide by sine squared theta. Okay? So sine squared theta and divide sine squared theta. Okay? And then we start simplifying. What's sine squared theta divided sine squared theta?
1.
1. Okay. Cos over sine. Well, we know sine over cos is tan.
Cotangent?
Yeah, that's right. Cos over sine would be cotangent. Okay, so we get plus, and because they're both squared, cotangent squared theta. And reciprocal of sine?
Cosecant?
Cosecant, right? So we get cosecant squared theta. And usually it's set equal to 1, so 1 is equal to cosecant squared theta, and then we bring the cotangent over, subtract cotangent squared theta. So all of these proofs, really, if you memorize this one here, and you know that I'm just going to divide by one of these, and I can remember my quotient identity and my reciprocal identities, I can build the other Pythagorean identities also. Okay?